In today's lecture, I'm going to be talking about annuities and gradients that differ from the standard, non-standard annuities and gradients. Now, you recall from previous lecture that there's a very strict definition of annuity, what an annuity is and what a gradient is. In an annuity, you have a series of equal amounts of value A over time, which start at the end of the first period. And moreover, the compounding period and the period of the annuity are the same. So we're compounding in each period, and the annuity occurs at the end of the period. With a gradient, it's similar. You have equally spaced over time. Gradient has two parts to it, the base annuity, A prime, and the gradient part, or parts, which is how they increase by the same amount each period. But again, the compounding period and the period separating each payment is the same. Now, there can be variations from these two standards in a variety of ways. One thing that can happen is that the timing of either the annuity or gradient can differ from the standard. The payment might not be beginning at the end of the first period. It might be beginning later or earlier than that. I'm not going to be talking about that in this lecture. I'll be talking about that in a later lecture. What I want to talk about in this lecture is where the compounding period and the payment period differ. And this is different from the standard and has to be dealt with in a special way. So for example, how much is accumulated over 20 years in a fund that pays 4% interest, compounded yearly, if $1,000 is deposited at the end of every fourth year? Now, what we have here is a payment pattern as illustrated in this diagram. We've got 20 years involved, but the payments only come at the end of each 4 years. So we have the payment in the fourth year, at the end of the fourth year, the end of the 8th year, the end of the 12th year, the end of the 16th year, the end of the 20th year. Now, one way of doing this calculation would be the obvious but time-consuming one of treating each of these amounts separately. Now, we want to find out how much is accumulated over 20 years. So what that really comes down to is taking this amount here and finding an equivalent amount that far in the future. Now, that's moving that money, if you like, over 16 years of time, converting what could be considered a present worth 4 years from now into a present worth that would be 16 years from then. So we take our amount of $1,000, move it forward in time at our interest rate of 4%, 16 years. And that will give us an equivalent for that particular payment alone. We could add to that the equivalent for this payment. For this payment, we're taking it through time a fewer number of years, converting it to a future worth from a present worth at 4% over now 12 years. And so forth. Taking this payment at the end of the 12th year, in the future 8 years, this one 4 years, and the last payment's already in the future, so we don't need to change it at all. If we perform that calculation, we'll get an answer by adding those things together. It's complicated, it's hard work, but it will give us the correct answer, and you'll see in your notes, in fact, that calculation done. But there's an easier way. And the easier way comes from recognizing that we can interpret this non-standard annuity in a different way. The problem with using our compound amount factors with this payment pattern is that we compound our money 4 times between each payment. But if we look at it a little bit differently, if we think well, let's renumber our periods. Let's consider every 4 years to be one period. We get a pattern of payments which then fits the standard, because we have a compounding period which is equivalent to the payment period. And this then fits the mold of a standard annuity. The only thing we're missing is the interest rate for these 4-year periods. Because the interest rate we're given of 4% is 4% compounded yearly. And that's not going to be the same. If we multiply the 4% times 4 periods in the year, they'll give us 16%. But that would be the same as a nominal interest for a yearly interest rate. It wouldn't be really the actual interest, because the compounding occurs within each of those 4 periods. But using the model of a nominal and effective interest, what we can do is calculate an effective interest for that 4-year-long period. We can do that using our effective interest formula, which was, of course, developed for yearly periods. The idea is, mathematically, there's no difference between a 4-year period, as in this diagram, and a 1-year period of 4 quarters. So if we consider that 4% being the interest rate per quarter and calculate an effective interest rate from it for a year period, that's the same as calculating a 4% per year period for a 4-year period. Now, recall our effective interest rate formula. We calculate the effective interest rate as 1 plus, now the expression here is R over M, where R is the nominal rate, M is the number of periods in a year. What that R over M really means is the interest rate per small period, per quarter, per month, or whatever it is. We have that in our problem of 4%. We don't have an R, we don't have an M. We can just use that 4% directly. Raised to the M is the number of periods in a year. In this case, the equivalent would be the number of years in our 4-year period. So that's the 4th, then minus 1. So I'm using our effective interest rate formula, but in a way different from what it was developed. It was developed for small periods within a year. Here I'm using it for years within a larger period larger than the year. The mathematics is the same either way. And then working this through gives us the effective interest rate of 16.99% for our 4-year period. We can then use our series compound amount factor to calculate the future worth. It's going to be the 1,000 S/A at 16.99% over the 5 4-year periods. Right? 1, 2, 3, 4, 5. And calculating that out gives us 7013. And it turns out, as you can see in your notes, that 7013 is identical to what we could calculate using by moving the individual payments forward in time, one at a time. So this is very handy, and this is the natural way of taking an annuity or a gradient that's non-standard in the sense that it has a different compounding period from the payment period, and rationalizing it by converting the compounding period to be the same period as the payment period. Now, in subsequent lectures, we'll be talking about other non-standard annuity ingredients, particularly an annuity due and displaced annuities and gradients. Thank you.